Today's topic is of immense importance to both the environment and our health. It is a series of chemical systems that limit possible damage and hence are called buffers. A buffer system is a mixture of compounds that minimise the effect of additions of acids or bases. I'll show you what I mean. So here we are in one of the teaching labs at the University of Plymouth. Here I've got two beakers, both containing about 100 ml of solution. In one I've got a fairly concentrated buffer solution. It has a pH of 4.45. In the other I've got some water which I've acidified slightly to get to the pH to roughly the same level. To the beaker containing slightly acidified water, I'm going to add 1 drop of 2 molar hydrochloric acid. And you can see that the pH changes markedly from 4.48 down to 2.93. A large change in pH. To the beaker containing the buffer system, I'm also going to add 1 drop of hydrochloric acid. And you can see that there's a very small change in pH, possibly 0.01 of a pH unit. The buffer system has minimised the effect of the addition of an acid. Let's see how this works. The buffer system was made up of a mixture of two compounds. One was ethanoic acid. This is a weak acid. In other words, the majority of the molecules don't dissociate. They stay as molecules, not ions, in solution. If this was the only compound in the solution, a good estimate would be that 99% of the ethanoic acid exists in solution as neutral molecules, and about 1% exists as ethanoate ions and hydrogen ions. The other component of our mixture was sodium ethanoate. This is almost the same molecule as ethanoic acid, but the hydrogen on the acid group has been replaced by a sodium ion. This means that all of the compound dissociates in water. 100% of this material exists in solution as ethanoate ions and sodium ions. Because the addition of the sodium ethanoate raises the concentration of the ethanoate ion, the equilibrium of the ethanoic acid is pushed back to the left. To a very good approximation, we can say that all of the ethanoic acid exists in solution as undissociated molecules. This means that our buffer solution contains lots of molecules of ethanoic acid that could release hydrogen ions if the circumstances change, and lots of ethanoate ions that could react with hydrogen ions if the circumstances change. If we cause change by adding some acid, the concentration of hydrogen ions in our solution goes up. But there are lots of ethanoate ions in solution. These react with the hydrogen ions to form molecules of ethanoic acid. This decreases the hydrogen ion concentration to almost its previous value. This is how this buffer system minimises the effect of adding an acid. But what happens if we add a base? So here I've got another two beakers. In one, the same buffer as before, showing a very similar reading, this time of 4.44, and another beaker of slightly acidified water, showing a very similar pH reading of 4.49. To the beaker containing slightly acidified water, I'm going to add 1 drop of 2 molar sodium hydroxide. The pH changes very markedly. I'm also going to add 1 drop of 2 molar sodium hydroxide to our buffer system. And it doesn't change at all. Here's the buffer system set up as before. When we add a base to an acidic buffer system, 2 reactions are possible. The first is that the base reacts directly with the undissociated acid, ethanoic acid in our example. This neutralizes the base and minimizes the change in pH. The second is that the base reacts with hydrogen ions in solution to make water. When this happens, the weak acid equilibrium moves to release hydrogen ions into solution, replacing those that were lost. So this is how a buffer system minimizes changes in pH. Remember that these systems are based on equilibria and hence they minimize change, not stop it completely. Also, any buffer is limited. If you add too much acid or base, the system will just run out of reagents. Buffer systems can be acidic or basic depending upon the compounds used. Now, I started this video by saying that buffers are important to our health. This is because blood contains compounds that act as a buffer system, stabilizing the pH close to 7. If the pH of your blood changes too much, your life can be in danger. I also said that buffer systems are important in the environment. Behind me is the world's largest buffer system. The ocean covers more than 3/4 of the planet's surface, and it uses multiple chemical systems to provide that buffer. The main system uses carbonate and hydrogen carbonate ions. If acid enters the system, the equilibrium moves to the left. If base enters the system, the equilibrium moves to the right. Of course, we've been putting this to the test, unknowingly until recently. We've produced about 1.5 trillion tonnes of CO2 since the start of the Industrial Revolution, and about 40% of that has dissolved in the ocean. Fortunately, the buffer system has minimised these effects. Minimised, but not eliminated completely. Today, the pH of seawater is about 8.1. Before we started burning lots of fossil fuels, the pH was about 8.2. Now, this may not sound like much of a change, but because the pH scale is logarithmic, that means the hydrogen ion concentration has increased by about 25%. If you are a marine organism, especially one with calcium carbonate shell, the ocean has become markedly more acidic.